Hello everyone, welcome back to the fourth lecture of week 11. In this week, we had explored definite integrals, their concepts, their mathematical derivations as two types. The first type was as the antiderivative of a function, right? So, and the second type was definite integral as limit of sum. Here, we are adding the reverse way, that means definite integral as limit of sum. And if the question or problems are given in series, summation of series, then how I can solve those summation of series using the different integral. So it's just a reverse type of thing. So we are going to explore these two things. In the previous lecture, we have seen that the integral as the limit of a sum, where we have find out that for a given closed interval a to b, we can write down as we can have the partition n partition, and we had find out the length of each subinterval equal partition as h, and henceforth n into h is nothing but the length of the closed interval ab. And similarly, this is the same thing as I can write this one as a lower limit a to upper limit b and f of fx dx. It is exactly the same area it has given, that means exactly equal to, if I took this limiting function n tends to infinity, h of fa plus of f of a plus h and so on, right? And all these a and a plus h, a plus 2h and so on, all these are the node points of this one, right? So we had seen this one, but we have not proved that one. So in this lecture, I am going to prove this using the fundamental theorem of integral calculus. And what is the fundamental theorem of integral calculus? It is said that if f is a continuous function in a closed interval ab and differentiable in an open interval ab in a finite domain ab, then d capital F by dx is equal to a small fx. If it holds, then this implies a to b, that means integral of this fx dx is equal to fb minus fa, and this is equal to limiting value of n tends to infinity h into fa plus h plus of fa plus n minus 1 into h, and where h is nothing but b minus a by n. So that is the fundamental theorem of integral calculus, where you had find out you have a limiting value, that means you are messing with a to b as a function in finite strips, right? And the integral is going to be the some function, some value area under the axis and the function curve. So that was the idea, and let us prove this theorem using the concept behind the definition of a derivative. So what was the derivative of a function? So if x, if I want to derive as the derivative of this function, I need some perturbation. So I will give h as a perturbation in x, and henceforth the function is perturbed and will be fx plus h. So how much the difference in argument of this function? So that means the difference between these two, that means f of fx minus f of x divided by h. Now this quantity, if I took this difference h is going to be 0, this will give me exactly the derivative of the function fx at the point x, right? So this will be nothing but this will be the derivative of the function at the point x itself, right? Now, since this limiting value, that means there are some perturbation and leads to some differences. So without, if you want to remove this limit from the left hand side, you need to add something in the right hand side, and that is the beauty of this calculus things. So how much the value? Now if fx plus h minus f of x divided by h, and I want to write without limiting value. So if I want to remove, or if I want to eradicate the limiting value of left hand side, then this must, I have to add something. So f dash of x plus of some epsilon here, right? This epsilon has only came due to the limiting value in the left hand side. So where epsilon tends to 0 and when n tends to infinity, and so h tends to 0, giving to x the values a plus h, a plus 2h in succession, right? And so we get capital F a plus h minus f a equal to h into f a, and f a plus 2h is minus f a is equal to h into a plus n, and so on, right? So that means all these you have 2 epsilon into f of a and so on. So here it's written epsilon into epsilon and so on, right? So h into f a plus n minus 1 into h plus of h into epsilon, because you had already find out that the differences between the capital F x plus h minus f x divided by h is nothing but this is the small f dash of x plus epsilon. Don't be confused with the capital F and the small f. Capital F is the antiderivative while a small f is the derivative of that function. So these two are the quite different things, and these two you can say the opposite things. So remember this one, left hand side we are keeping capital F, while in the right hand side we are keeping it's a small f, that is the derivative things of the function. So function itself, and this will give you f b minus f a. I mean you have to just cancel each out like this, like this, like this, like this, and so on. So what you have left? You have left minus f a and f a plus n h, and f a plus n h, that means a plus n h is equal to cap b. So that means f b minus f a. So this is nothing but this is a plus n into h minus f a, right? This is the same thing, and that is equal to left hand side always consists of a small h, not the capital H. So h into a small f a plus f into a plus h plus f a plus n minus 1 into h, and plus how many error terms, or you can say the limiting term you are adding. So h into epsilon 1, h into epsilon 2, h into epsilon 3, and so on. These has been left. This is a typo, you have to rectify it. So that means taking common as h, you will get the epsilon 1 plus epsilon 2 plus epsilon 3 and so on till epsilon n. And let epsilon r be the term in epsilon 1 plus epsilon 2 plus epsilon n, which has the largest numerical value, right? So I assume that epsilon r be the largest numerical value. Then h into all those in the modulus epsilon 1, epsilon 2, epsilon n, it must be less than or equal to h into n of epsilon r. Why? Because we had done h into epsilon 1 plus h into epsilon 2, right, plus h into epsilon 3 and so on, plus h into epsilon n. How many terms you have? You have n terms, 1, 2, 3 to n. So n terms there are n terms here, and each term is less than or equal to which one? H into epsilon r. As you have supposed that epsilon r is the greatest one, the largest numerical value. That's why h into epsilon r is the, each term is less than of this, right, is each term. So that means the whole quantity is less than or equal to how much? H into epsilon r, and how many times? N times. So this is the answer, right? So that's what we had written here, and this is less than or equal to how much? H is nothing but this one was h into n equal to b minus a. So that means the b minus a into epsilon r. That is, as h tends to 0 and epsilon r tends to 0, hence b minus a into epsilon r is also going to be 0. So what you will get? You will get h into epsilon 1 plus epsilon 2 plus epsilon n is going to be 0, as h going to be 0, right? So the theorem to be proved now follows from the equation 3 here on taking limit as n tends to infinity. So now we are taking n tends to infinity here. As you can see, n tends to infinity, that means h is going to be 0. That is the same thing, either you are saying n tends to infinity or h tends to 0. So, in the above definition, we have divided the range of integration b minus a into n equal intervals and taken 1 in the value of the function fx at the beginning of each interval. This is not really necessary. We may divide the range b minus a into n unequal subintervals and something like delta x1, delta x2 and delta xn and take the sum of this one, right. So, where xr is the value of x any point in rth interval delta xr, and it can be shown that the limit of the sum of 4 as n tends to infinity and the length of each interval delta xr tends to 0 is the same as the limit of the sum in equation 1, right. So, it does not matter how you are dividing your given interval, right. So, it is not necessarily that you are taking n equal subintervals, n unequal subinterval also doing the same thing, and we will reach at the same conclusion as 1. Now, remark 3, the fundamental importance of this theorem is that it avoids having to integrate a function from the first principle as the limit of sum. If capital Fx be the antiderivative of the function can be found, the definite integral can be easily evaluated at the two endpoints of the range of the integration. Various problems of geometry such as determination of areas require integration as limit of a sum. Historically, the sign of integration is merely the old form of S, that means the area, and the initial word of the word is sum. So, that is what history says, that the integration is nothing but it is the sum, limit as a sum. So, this is the first example we are going to use for definite integral as the limit of sum. So, evaluate a to be x square dx by expressing as the limit of a sum. So, remember this one, the formula says that either limit tending to n to infinity h into fa plus of fa plus, so I will write your equation for you. So, f of x dx is nothing but limit value n tends to infinity h into f of a plus of f of a plus h and so on, f of a plus of n minus 1 into h, right. This one was the formula. So, I am going to use this one here. F of x is given, f of x equal to x square, henceforth f of a is equal to a square. Similarly, f of a plus h is nothing but a plus of h ka whole square, isn't it. You have to put in place of x a plus h, a plus 2h and so on. So, the right hand side, that means the integration from a to b x square dx can be written as limiting value n tends to infinity into h a square, that is fa, that is fa here, this is f of a plus h and so on, right. And always remember that n into h is nothing but it is the length b minus a, right. So, this will give you limit n tends to infinity h into a square and a plus nh. So, n a square here, a into n square plus 1 plus 2 plus 3 to n minus 1 into 2ah plus 1 square, 2 square and so on, n minus 1 ka whole square into h square. That is the simplification of these terms. So, you just simplify it using the given formula, and this will give you once again, this will give you, again we have to simplify it. So, limit n tends to infinity nh a square half of nh into n minus 1 into 2a ha 1 beta 6 of n minus 1 to n minus 1 nh square. And how we had reached at this conclusion? See, this is the n minus 1 term and the sum of this natural numbers. So, what is the formula? That is the n into the next term. So, n into n minus 1 divided by, see here, n into n minus 1 divided by 2. And similarly, you have this one 1 square, 2 square and so on. And this will be easily find out that n into n minus 1 divided by 6, right. And that is how we have built it here, n minus 1, right. So, this is n I mean, you can find out n minus 1 into 2n minus 1 into n divided by 6. And now simplify all those. So this will give you nh square, and 2 is the cancel out here. So this will be nh into n minus 1 into ha, and here you will find out 2. So you can have this 2 common outside of this bracket. So this will give you 2 into n by 1 by 2. So that's become the 3. So 1 by 3 into n minus 1, n minus 2 into nh square. So nh is nothing but b minus a. nh is nothing but b minus a. And here nh square. So you can take this nh, and this will give you n minus 1 into n minus 1 by 3. So this is nothing but b minus a ka whole. So as you can see that whenever you simplify the equations, it will comes out in length. That means the given closed interval a and b. So we had find out b minus a ka square, b minus a ka whole square into a, 1 by 3 b minus a ka whole cube. Now simplify all those, and taking b minus a common from each side, you will find out b minus a here, and since 1 by 3 is the taking common, so 3a square, right? And here 3b minus a, you are taken once only, so b minus a into a, and here it will comes out to be b minus a ka whole square. So b square minus 2ab plus of a square. This is nothing but b minus a ka whole square, right? And then simplify all those equations. As you can see here, 3a square, 3b minus 3a square here. So that will be the cancel out. Similarly, b square minus 2ab plus a square, meeting here 3b into a. So you will have this simplification, and you will find out a square plus of ab plus of b square. And this is quite easy to do this. Now simplify once again, and it will comes out 1 by 3 into bq minus of aq, and that's your answer. So as you can see here, we had find out the abx square dx, the different integral of a to b, that means x square dx, as the limit of sum is nothing but 1 by 3 b square minus a square. Can I use the antiderivative, and can I verify my results? Yes, you can. So now what will be the, let me verify here. So the function is given as x square. What will be its antiderivative? Obviously this will be the x cube by 3, right? And so a to b x square dx is nothing but you have the antiderivative here, and this will be going to be from a to b. What will be the value? That will be bq minus of aq. And as you can see here, this is the same as here, right? So that means the definition of a different integral or formula given in the different integrals from an antiderivative perspective, as well as the different integral as limit of sum, are quite easy. Now this one has been, I mean, already explored in the last sections. So now what we are doing to do in this lecture, we are trying to find out some of the questions, some questions such that it containing a lots of terms, that is, it may given as a series, and we are going to find out the summation of the series as using the different integrals. That is the beauty of this different integral concepts. So here is the new concept for the different integrals. So what it says, that definition of integral as the limit of a sum enables us to express the limits of a sum of a series of a certain type as different integrals, and thus to evaluate them. The value of the required limit can be written down by the formula 5.4, that one. So r equal to 0 to r equal to n minus 1, f of a plus rh into h, and limit n tends to infinity, right? That was our formula here. See, oh, here I have written this one. Did this see? Limit n tends to infinity h into this one, and that is equal to the different integral a to b fx dx. And remember that one, that B minus A is nothing but this is N into H. N is the equal interval or unequal subinterval, both are the same. So more conveniently, by the formula derived from the above by putting A equal to 0 and B equal to 1. So B equal to 1 minus 0 equal to N into H. So 1 equal to N into H, right? So H is nothing but 1 by N. This is good, good numeric values for H. So H is now 1 by 10. So whatever the N you are taking, just the reverse will be your small h. So this formula is now become, as we have put it, B equal to 1 and A equal to 0, is now become, this will give me 0 to 1 fx dx. So if I have, and this one has been derived as r equal to 0 to r equal to n minus 1, f of r by n, because A is become 0 and r into h, h is equal to 1 by 10, so r by n, and h is equal to 1 by n. So that means if I have a certain type of the series such that the function, it can be written in a function f r by n to 1 by 10, I can find out these summation of this series as a integral, different integrals, and that is the huge things for mathematicians to go ahead. So properties required for a series to be summed by this formula are: it must be possible to write the terms of the series in the form of 1 beta n into f of r by n. So terms must be written in that form, so that 1 beta n, which tends to 0 as n tends to infinity, is a factor of every term, and all the terms are functions of r by n, which varies in the value from term to term in arithmetical progression with the common differences as 1 beta n, right, h, right. The number of terms should be n, but since each term tends to 0, the addition or omission of one or two terms or any finite number of terms will not alter the final results. So working rule, so I am just putting down the working rule. Write the series as 1 beta n into f r by n and take as required, the required limit is limit n tends to infinity 1 beta n f r by n. To write down the corresponding different integral, replace r by n by x and its common difference 1 beta n by dx. So what it will become? It will become the, and limit of sigma is by summation. So it will become integration of f of x dx. So insert the value of r by n for the first and the last terms or the limits of such value as the lower and upper limits respectively in the integral. First term as the lower limit and the last term as the upper integral. This procedure will evidently give us integral of fx dx taken between the proper limits, right. So now we are going to, so what we have done? We have done limit of summation sigma is taking as integral sign r by n as x, right. So f of r by n is equal to f of x, 1 by n is dx, right. That means the whole summation can be written in a integral, different integral signs with the proper. So the first example, as you can see here, find the limit as n tends to infinity of the sum. It is not given that you are going to use the integration or not, but since the structure of the already series of the terms of the series in such a way that I can convert this whole series as a summation, limiting of summation values, and that will gives me the integral part. So look at r plus 1th term in this series. What was the rn plus 1th term? So n by half is the constant above, and each term, see, this is the first term, this is the second term, this is the third term, and so on. So n plus 3 are 3 by 2, right. And that means I can write this one taking 1 by 2 as the indices as a common factor and cancel it out. So this will gives me 1 beta n divided by 1 plus of 3 rn, 3 r by n, 3 by 2, right. So that's what we have done. So therefore require the value of what this question has been converted in the summation in a limiting sense is limit n tends to infinity, summation n minus 1 r equal to 0 to n minus 1, 1 by n, 1 plus of 3n, 3r by n, 3 by 2. Here 1 by n, now I will convert this one in integration. 1 by n is equal to dx, 1 plus of 3r by n, 3 by 2 will be the our f of x, right? And the limiting value here from r equal to the first term to last term will be the upper limits and the lower limits. So this will comes out d of 1 by n is dx, f of x equal to 1 plus 3x 3 by 2, right? Because you have 1 plus 3 r by n, r by n equal to x. So putting this one and limiting value from where to where? 0 to 1, right? So that's what we have done, and it can be easily evaluate this integral value. So how much the integral value? You can evaluate from here. So 2 divided by minus of 2 divided by 3, 1 plus 3x, I mean 1 by 2, so 0 to 1, this will gives you 1 by. So now as you can see that the series which has been looking like a big complex mathematical complex objects is now become quite easy in a integration sign. It's a different integral from 0 to 1 of a one function, right? And this will gives me 1 by 3. So that the idea, and idea was quite easy to do that, and you can put this one as well. Use the definition of integration as limit of a sum and evaluate this. Already given limit n tends to infinity of this series. So I can put this one and rewrite the series. So first term is 0, second term is n plus 1, n plus 2, n plus 3, n plus 2, n plus 0 is the first term. So that means rth term is nothing but 1 by nr. 1 by n plus r can be written as 1 by n as a common, because I need 1 by n. 1 by n is given me the dx, and from where to where? So this will convert in containing this convert rth term of this series containing 1 by n and 1 by 1 plus of r by n, right? So r by n is equal to x, 1 by n is equal to dx, and the range is from 0 to 2n. So using this one, this will comes out like limit n tends to infinity r equal to 0 to 2n, 1 plus of 1 plus rn and 1 by n. So using this one, you will find out 0 to 2 dx 1 plus x, and what will be the value? The value will be the log 3. So that's the easy thing to do this. Similarly, as you can see here, limit n tends to infinity tan pi by 2n, tan and so on. So what I have to do? I have to find out, since it is in the product of each terms, right? So I will convert it in the addition or summation of the each term, and to convert it taking the log of this one. So let's say a equal to this one, and then taking the log both sides, you will find out that the integral becomes I equal to 0 to pi by 2 log of tan t dt then. And so this will comes out to be 0. And that's your answer, right? So as you can see here, tan pi by 2n, tan 2 pi by 2n, tan 3 pi by 2n, and so on, and 1 by n in this is going to be 0. So that's a very easy to easy things for us. It makes the situation in a very good thing. So this will give me log of a. So log of a equal to 0. So this means the limiting value is equal to 1. So here is the a value is equal to 1. So similarly, we can find out 1 plus of 1 by n doing the same process, and as you can see here, this will be going to be e to the power pi squared 12 divided by 12. So that is our calculations. I believe that this summation and the summation of a series as an integral will enhance your ability to take the problem in such a sense where you will evaluate the integral values. So I hope that it will enhance your concepts. So thank you so much.